What happens when a star dies but refuses to fade? It collapses into something so dense, so alien, that even atoms break. Welcome to neutron stars, where physics unravels and gravity reigns. A teaspoon weighs more than mountains, a magnetic field stronger than anything in the universe. This is nature's most extreme experiment, born from death, powered by light. Let's explore the science of neutron stars. Every neutron star begins its life in chaos. Imagine a giant star, at least 8 times more massive than our Sun, burning bright for millions of years. Inside its core, nuclear fusion keeps it alive, hydrogen fusing into helium, helium into carbon, and heavier elements one after another. But eventually, the fuel runs out, and when fusion stops, the delicate balance between outward pressure and inward gravity collapses. Gravity wins. In a fraction of a second, the core of the star implodes. Temperatures soar past 100 billion degrees. The outer layers are blasted away in a supernova explosion so powerful that for a brief moment it outshines an entire galaxy. What's left behind is not a planet, but a black hole for something in between. The core crushes under its own weight, forcing protons and electrons to merge into neutrons. Matter as we know it ceases to exist. The result is a neutron star, a sphere just 20 kilometers wide, yet heavier than the Sun. The explosion fades, the dust settles, and in the silent aftermath, this tiny object spins, fast, furious, and impossibly compact. Its very existence a warning to the universe that death can sometimes create something even more powerful than life. Let's put that into perspective. If you could shrink the Sun down to the size of a city, it would still be too big. A typical neutron star is only about 20 kilometers in diameter, roughly the size of Manhattan. But inside that small volume lies more mass than 330,000 Earths combined. If you could scoop up a single teaspoon of neutron star material, it would weigh around 1 billion tons, the equivalent of all human-made buildings on Earth compressed into a spoon. And that's not even the strangest part. The surface of a neutron star isn't solid in any familiar sense. It's a bizarre hybrid of atomic nuclei and free neutrons, forming a crust so dense that a mountain on its surface could only rise a few millimeters before collapsing under gravity. Beneath that crust lies the true heart of madness, a superfluid ocean of neutrons that move without friction, swirling like ghostly quantum waves. Deeper still, scientists suspect there could be exotic matter, particles that don't exist anywhere else in the universe. Perhaps even quark matter, where neutrons themselves break apart into their most fundamental components. If that's true, then deep inside these stars could lie the building blocks of everything, stripped bare, raw, and pure. Now, just take a moment and think that the star that collapsed didn't just fall, it spun. And because of the conversion of angular momentum, that spin became unimaginably fast. Just like an ice skater pulling in her arms to spin faster, a dying star rotation accelerates as it shrinks. The result is a neutron star spinning hundreds of times per second. Some rotate faster than a kitchen blender. These are called pulsars, rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. As the star spins, those beams sweep across space like cosmic lighthouses. And when one happens to point directly at Earth, we see a rhythmic pulse of radio waves. Click, 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 so precise that scientists use them to measure time more accurately than atomic clocks. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell. At first, no one believed it. The regular pulses were so perfect that astronomers half-jokingly labeled it LGM-1, Little Green Men 1, thinking it might be a signal from aliens. But the truth was even more fascinating. They'd found a rotating neutron star, a natural clock forged in the death of a sun. Today, we've catalogued thousands of them, each with its own rhythm, each a ticking reminder that the universe still holds mysteries we're only beginning to count. But some neutron stars go beyond even that. They don't just spin, they warp reality itself. These are magnetars, the most magnetic objects known in the universe. Their magnetic fields are 1,000,000,000,000 times stronger than Earth's, powerful enough to distort the very shape of atoms. If a magnetar appeared halfway to the moon, it would wipe every digital device on Earth clean in an instant. Magnetars are born from stars that collapsed with extreme rotation and magnetic turbulence. Inside them, magnetic energy builds and twists until it snaps, releasing bursts of gamma rays so intense that even from thousands of light years away, they can disrupt satellites and ionize our atmosphere. In 2004, one such burst from a magnetar named SGR 180620 hit Earth. It lasted less than a second, yet it released more energy than the sun emits in 100,000 years. If it had been any closer, it could have stripped away our ozone layer. And yet, these monsters are only about 20 kilometers wide. Think about that, a magnet the size of a city, with the energy to shake a solar system. It's almost as if the universe built these things just to remind us how fragile we really are. Neutron stars are more than just cosmic curiosities, they're laboratories, natural test sites for physics so extreme we can't replicate them on Earth. Inside them, matter is compressed to densities beyond what atomic theory can comfortably explain. Greater relativity predicts their structure should hold, but quantum mechanics disagrees. Somewhere inside these stars, the two pillars of modern physics collide, and we don't yet know which one bends first. That's why astronomers watch neutron stars so closely. Their collisions, known as kilonovae, produce gravitational waves, ripples in space-time first detected in 2017 by LIGO. When two neutron stars spiral into each other, they unleash forces that forge the universe's heaviest elements: gold, platinum, uranium. In that moment, the cosmos literally makes treasure from destruction. So, the gold in your ring or necklace? It may have been born in the death throes of two colliding neutron stars, a reminder that even violence in the universe can create beauty. But these collisions also reveal something deeper. By studying the exact shape of the gravitational wave signals, physicists can infer how squishy or stiff neutron star matter is, clues to the mysterious equation of state governing matter at nuclear densities. Every event brings us one step closer to understanding the ultimate frontier of matter. Though neutron stars are tiny, they can light up the cosmos. When they accrete material from a nearby companion star, that gas doesn't just fall, it spirals in, heating up to millions of degrees and releasing powerful X-rays. These systems, called X-ray binaries, are some of the brightest objects in the sky, and sometimes when that infalling material builds up and detonates on the surface, it creates X-ray bursts, nuclear explosions that momentarily outshine an entire galaxy. For astronomers, each flash is like a coded message, a clue to what's happening deep within that ultra-dense surface. Even without companions, isolated neutron stars continue to glow faintly, cooling slowly over millions of years. Some move through the galaxy at breakneck speeds, kicked by the blast of their birth, racing across interstellar space at over 1,000 kilometers per second. Each one a rogue ember of a dead star, whispering the story of creation and collapse. At the heart of every massive star's death lies a coin toss between two outcomes: neutron star or black hole. The deciding factor? Mass. If the collapsing core is between about 1.4 and 3 solar masses, it stabilizes as a neutron star. Anything heavier, and gravity crushes it beyond even neutron degeneracy pressure, forming a black hole. This threshold is called the Tolman-Oppenheimer-Volkoff limit, the point where even neutrons can no longer resist gravitational collapse. Beyond that, space-time folds inward, and no force known can stop it. But what happens right at that limit is one of astrophysics' greatest mysteries. Could there be something between a neutron star and a black hole? A quark star, perhaps? A phase of matter so dense that quarks themselves are liberated from their confinement? We don't know yet, but every observation, every gravitational wave detected, is another step toward the answer. In many ways, neutron stars are the perfect bridge between the tangible and the unknowable. They are as close as we can get to touching a black hole without falling into one. As telescopes grow sharper and detectors more sensitive, we're entering a golden age of neutron star science. The James Webb Space Telescope has begun detecting the faint infrared afterglows of kilonova explosions, while radio observations like FAST in China and the Square Kilometre Array are mapping thousands of new pulsars. Each discovery helps refine our understanding, not just of stars, but of physics itself. Because at their core, neutron stars are a riddle written in gravity. They compress the entire periodic table into a sphere, fuse death into light, and test the limits of spacetime. The more we learn about them, the more we realize they are not just remnants of stellar death. They're the keys of understanding life itself. The carbon in your cells, the iron in your blood, the gold in your ring, all of it was forged in stars like these, born in fire and scattered across the universe by explosions we can barely comprehend. We are, in the most literal sense, the descendants of dead stars. But neutron stars, those are the ones that refuse to die quietly. They are cosmic ghosts, spinning endlessly, telling the story of how the universe builds beauty from destruction. So, the next time you look up at the night sky, remember, hidden among those distant pinpricks of light are objects smaller than a city, yet heavier than a sun. Objects that warp space, twist light, and hold the answers to physics itself. They are neutron stars, the universe's ultimate paradox, born in death, small yet infinite, silent yet thunderously powerful. The extreme science of neutron stars reminds us of one truth, that even in the coldest, darkest corners of space, the cosmos is never done creating wonder. Like, subscribe, and stay curious, because the universe still has stories left to tell.